Welcome. This is the Cisco CCNA ENSA, also known as the Enterprise Networking Security and Automation course. This course focuses on the CCNA version 7 curriculum. This is course 3 of 3. Alright, let's move on to traffic characteristics. So looking at network traffic trends, basically early 2000s, predominant IP was voice and data, phone calls, and web content. So to look at those characteristics, the voice had a predictable bandwidth need and a realistic round-trip travel time. Data traffic wasn't real-time, so it wasn't really that important. It was unpredictable in bandwidth needs also. So data traffic could be temporarily bursted with larger files being downloaded. That burst essentially means it could go really fast and slow, then fast, then slow. That way, in between the faster bursts, they could jam-pack other type of traffic. But however, more recently, it's becoming increasingly important for businesses to actually be able to provide basic communication and operations. So according to the Cisco Visual Networking Index, the VNI, video traffic represented about 70% of all traffic in 2017. By 2022, video traffic is supposed to be 82%. So video being both voice and voice, audio, and a visual component. Essentially things like YouTube and other streaming services. They're going to be the majority of traffic on the internet. Mobile video traffic is going to be reaching 60.9 exabytes per month in 2022. Again, consuming visual and audio-based video content either through a mobile device or through a regular device on a data network. That means the type of demands that voice and video are putting on the network are very different than traffic. So when we're looking at the characteristics, those real-time components need to be able to be given a higher priority, but at the same time, we still need to be able to balance it between regular data and traffic with a real-time component. Alright, so let's look at voice. Voice traffic is predictable and smooth and very sensitive to delay and the jitter. Again, we do not want voice to be cut off in the middle of a conversation. So, traffic characteristics, we want smooth, we want it to be drop sensitive or delay sensitive. We want to be able to give it a certain level of priority. So there are specific requirements for voice. That is going to be latency has to be less than or equal to 150 microseconds. I meant milliseconds, not microseconds. The second microseconds popped up in my head, you could notice that I paused. Anyway, jitter has to be less than 30 milliseconds. And there has to be a total loss of less than 1%. Bandwidth needs to be about 30 to 128 kilobits per second per voice call. You have a call center with 100 people, it's not going to be 128 kilobits per second. It's going to be the bandwidth for each individual phone call added up. With video, and it can be bursty, though the traffic characteristic is it's very greedy in bandwidth. It also is drop and delay sensitive, and it also has a certain level of priority. Normally with voice, it will use UDP port such as 554. This is the real-time streaming protocol, RSTP. Latency should be less than 400 milliseconds. Jitter can be between 30 and 50 milliseconds. Loss, it could have a lot more loss than voice, but loss is going to be between 0.1 and 1% or less. And you'll notice that bandwidth is definitely drastically increased. Bandwidth is going to be per instance 384 kilobits per second through 20 megabits, but really just depends. If you're trying to stream an HD video, bandwidth consumption is going to be more. If you're trying to stream a 4K video, again, bandwidth is going to be greatly increased. So when we're looking at a network, if we're designing the network, we have to look at current characteristics and what are we going to be doing for growth, what's going to be allowed on that network, and if there are going to be any type of filtering. One of the jobs I work at, they actually limit video content like YouTube, and they drop it down to a very low bandwidth. That way you cannot stream HD, you cannot stream constantly. That way they can actually reserve some of that bandwidth for other applications. Anyways, so moving forward, we have our data. This is going to be any type of actual application type data, FTP or HTTP or HTTPS, DHCP or DNS. This is going to be the actual data that a user is going to be using. It can be smooth, it can be bursty, doesn't really matter. It can be benign, it could be greedy. Again, it doesn't really matter. It's drop insensitive and it's delay insensitive. Most of the time, data is going to be transmitted over over TCP. So if there is an issue, it just retransmits. So like FTP, for example. If a packet isn't received, big deal, retransmit. It may consume more bandwidth, but it doesn't matter. That delay in the receiving an additional packet is not that big of an issue. So since we said that data is relatively insensitive, does that mean it doesn't matter? It does matter. There's a quality of experience, or QoE, and it's the other important consideration with data traffic. Basically, it means is, does the data come from a interactive application? Is the data mission critical? If the data does come from an interactive application, that delay does matter. For example, let's say you're working in a database program and you're inputting data. And in order for you to hit enter, the program has to accept that data. If there is too much delay, then users may get frustrated. So, if it is a mission critical application, that insensitive, that interactive capability may lead to additional frustrations. That slower response time could be an issue. Normally, that's why they want you to strive for like a second-ish response time. If it's not mission critical, then again, you can lower the requirements and users just have to deal with it. If it's not an interactive program, the delay can vary because it really all depends on when the program needs to actually receive that data. If there is nothing that the user is interacting with, then it may not be considered as important. Alright, so let's talk about our queuing algorithms. So there are a few different types of queuing algorithms. First in, first out, weighted fair queuing, class-based weighted fair queuing, and low latency queuing. I know it says video, but again, we're just going to talk about all of them. So queuing overview. Basically with QoS, we could do a policy. So essentially what ends up happening is when we have a QoS policy, it will be implemented when an actual network admin decides to implement it. However, it may not always be active. It becomes active when there's congestion that's occurring on the link. And so what ends up happening is the queuing is going to be a congestion management tool that can be set certain criteria. Things like buffer prioritization and reordering of packets if necessary. So again, the admin sets up the policy, but the device determines when it's going to be active or not. There are a few different queuing algorithms that are used. First in, first out, weighted fair queuing, class-based, and low latency queuing are just some of the more common ones. So let's cover each one of these a little bit more in depth. So first in, first out. So basically, first in, first out queuing buffers and forwards packets in the order that they arrive. There is no prioritization. Whatever came in first, that's what goes out first, and so forth. The nice thing is, basically, everything is treated as equal. So the packets are sent out the interface in which the order they are received. So ingress and they egress the same order. The negative with that is what happens if there is a lower or a different priority. Well, FIFO doesn't really work like that. So we have a weighted fair queuing. This is more of an automated scheduling method that provides more fair bandwidth. They will create buckets essentially. And when enough packets come to fill a bucket in the ingress section, it will dump it and it will allow for egress. While the buckets for the lower priority traffic is a little bit larger, meaning it's going to only send when that container reaches a certain level. So the higher priority packets have a much smaller bucket. That way they're going to be dumped and be allowed to egress a little quicker. And again, buckets are just, or containers are just a concept here. Basically, we wait till there's a threshold, and once that threshold is met, send it on its way. That way it can collect. That way, when we're doing this, if we're receiving a ton of traffic, we can weight them accordingly. We also have what's called a class-based weighting fair system. This basically looks at our WFQ and expands it. We can look at traffic classes that are defined and match criteria, protocols, ACLs, input interfaces, and so forth. We could do packet satisfying the match criteria for forwarding. We could do a FIFO query is reserved for each class and traffic belonging to a specific class. And we can also look at a class that can be assigned characteristics such as bandwidth, weight, and maximum packet transmit limits. This basically will assign bandwidth to a class that's guaranteed bandwidth delivery. So it's always funny when I read that. Guaranteed bandwidth delivery. Bandwidth is X amount of a resource. Well, you can over-allocate that bandwidth. You can do guaranteed bandwidth delivery, but that means that bandwidth now is then sectioned off for only a specific set of channel. The problem with that is if nothing is on that channel, then what happens when the other prioritization packets are coming in that need that extra bandwidth? Well, if it's guaranteed, it can't be used for anyone other than what's destined on that channel. So there's some issues there. So here we have different classes. We have class 1, 2, 3, and these are all user defined. And again, what we do is we prioritize them, and as we get data coming in, we fill them into classes, containers, and then we forward them out when that class gets filled. So the tail will drop, discard any packets that are arriving at the tail end of a query that has completely used up its packet holding resource. Again, the packet holding are just what we call classes. When they get filled up, they get sent. We also have what's called a low latency queuing, LLQ. This feature brings strict priority queuing to our CBWFQs. Have to love the amount of acronyms when we talk about our queuing. Essentially what we do is we do our classes, but we also now have a priority queue. And the priority queue allows us to set very specific class priorities that will be sent ahead of our WFQs. Basically, if it is flagged as voice or video or the most important, when it looks at its queue and it looks at the WFQ, it is always going to send the priority queue first, and then it will send the WFQ. And with the WFQ, it will look at the user-defined class 1, 2, and 3 before forwarding it on. And that is it for this module. If you got any questions or concerns, please reach out. Thank you.